It has been reported by the U.S. Mint that 45% of Americans are collecting state quarters. Suppose that 20 Americans are randomly selected. Find the probability that exactly 10 collect state quarters. The first thing we need to do is recognize that this question can be thought of as a binomial experiment, because it can be imagined that this is done in trials. There are 20 of them because we're selecting 20 random Americans, so it's a binomial experiment with n equals 20, and the probability of success is 45%. So there's a 45% chance for each of these individuals to be collecting quarters. So success here means the individual chosen, does collect state quarters. So what we have is that this experiment is binomial, 20 trials, and a 0.45 probability of success. So to answer question 1, we want the probability that exactly 10 collect state quarters. We can do this with a formula. There are formulas for this, but we're going to instead ask GeoGebra to do the calculation. And we have a numeric answer, and we would like to ask for the binomial distribution, and you can see it's asking for the number of trials, which we just talked about, that's 20, the probability of success, which is 0.45, the variable value, that's 10, that's the number of successes we want to calculate the probability for, and this last item here, this last argument is Boolean cumulative. That means true or false. Do we want a cumulative probability? And in this case, we do not want a cumulative probability. We just want the probability of exactly 10. So, number of trials, 20. Probability of success, 0.45. We want the probability of exactly 10, and we do not want it to be cumulative. 0.15935. So again, we used binomial dist, 20, 0.45, 10, false. And that gave us 0.19. Sorry, 15935. Okay, and that is the probability. That's the probability of exactly 10. Number 2, the probability that at most 8 collect state quarters. So here we're looking for the probability of at most 8. That means less than or equal to 8. Well, that's exactly what a cumulative probability does. The cumulative probability calculates the probability of 0, 1, 2, 3, 4, all the way up to the number of interest. In this case, we want 8, so we want the probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, all added up. That's exactly what the cumulative probability does. So this time, we're going to say true at the end, because we do want a cumulative probability. The rest or at least the first two, are exactly the same. We still have 20 trials, we still have a probability of success 0.45, but this time we're interested in probability of x equal 8, or actually less than or equal to 8, so we have 8 and true, and that gives us, well, we'll find out in just a minute. So binomial dist, we want 20 trials, 0.45 probability of success, 8 is our variable value, and we do want it to be cumulative this time, so 0.4143. So this gives us an answer of, whoops, 0.4143. Number 3. Find the probability that at least 7 collect state quarters. So here we want the probability that x is greater than or equal to 7. Now, the binomial the cumulative probability will always count from 0 up to your number. So, in this case, we want to know the probability of 7 or more. So 7, 8, 9, 10, 11, 12, all the way to 20. But what we know is the probability that x is 20 or less is 1. So, we want 7, 8, 9, 10, 11, 12. So we add all of them from 0 to 20. Let me give a little diagram here. 16, 17, 18, 19, 20. Okay, we're interested in the probability of at least 7. So we want to add up the probabilities of each of these all together. Okay, but the binomial dist function doesn't give us 7 and up. It gives us from 0 up to a number. So what we really need to do is take the probability of all of them from 0 to 20. So the probability from 0 to 20 we know is 1, because that's the only thing that can happen. These are the only things that can happen. So the probability of any one of them is 1. And then the binomial dist function can give us the probability from 0 to 6. And we can subtract that from 1 to get the remainder, which is what we're after here. So, to summarize, what I'm saying here is the probability of x greater than or equal to 7 is exactly the same as 1 minus the probability of x less than 7, which is exactly the same thing as 1 minus the probability x less than or equal to 6. And this is a number we can calculate using GeoGebra. Probability of x less than or equal to 6 is just a binomial dist with a cumulative probability. So we'll do that. 1 minus binomial dist (20 trials), 0.45 probability of success, variable 6, and true. So 0.87007. So 0.8701. 0.8701. Number 4. Find the probability that between 5 and 11, including 5 and 11, collect state quarters. Okay. Number 4. We want the probability of x being between 5 and 11. Well, that's exactly the same as the probability that x is less than or equal to 11 minus the probability that x is less than or equal to 4. And again, I can draw one of these little diagrams here. It's because here are our choices: 5, 6, 7, 8, 9, 10, 11. If we calculate the probability of all of these happening, or any one of these happenings, that's this, and then we subtract out this part from 0 to 4, subtract that out, what's left is the probability of 5, 6, 7, 8, 9, 10, 11, exactly what we want. So this is how we do it, and these two are GeoGebra commands with cumulative probabilities of 11 and 4. So we hop over to GeoGebra again. We got binomialDist 20.45, 11 true, minus binomialDist 20.45, 4 true, and 0.8504. 0.8504. If many groups of 20 are selected, on average, how many people in each group are expected to be collecting state quarters? So number 5 is really asking us for the expected value, which we have a formula for, and it's simple enough. We'll just use it. Mu equals n times p. So this is the expected value, is the number of trials times the probability of success. In this case, that's 20 times 0.45, or 9. So we would expect on average 9 people of 20 to be collecting state quarters.